Welcome back, and this is the first in a series of packs looking at equilibria. Equilibria tells us how much. It gives us an idea about the position of equilibria for different reactions. It sits alongside kinetics, which tells us how fast. So for this topic you're going to need your pack, a pen and a calculator. I'm going to go through the theory. In the class we'll be going through the practicals, so I'm going to skip out those pages. So the first thing we need to appreciate is that some reactions are reversible. So a reversible reaction is one that can be made to go in either directions, forwards or backwards, depending on the conditions. So you've seen this first reaction before. We have anhydrous copper sulfate, which is this white powder. If you add water to it, it will turn it into these blue copper sulfate crystals. If we heat these blue copper sulfate crystals very carefully, we can drive off the water and turn them into this white powder. So that's an example of a reversible reaction. We show that using this symbol here, an arrow pointing in both directions. Other examples that you've come across is the thermal decomposition of a group 2 carbonate. That can decompose into the oxide and carbon dioxide, but that reaction is actually reversible. Another reversible reaction you've come across is sulfur dioxide reacting with oxygen to form sulfur trioxide, SO3. Again, that reaction is reversible. Lastly, one you've come across a lot at GCSE level, and that is nitrogen and hydrogen reacting to form ammonia. That's known as the Haber process, and it is also reversible. So skipping out the practical, which is on page 3, we're moving on to page 4, and we're looking at dynamic equilibria. So in order to reach equilibrium, the first thing that needs to happen is the system needs to be closed. In other words, we can't let things escape. If we have an open system, then stuff will escape from my reaction and it'll never actually reach equilibrium. The second thing is it needs time to reach equilibrium. Also temperature and pressure, or concentration, if I'm dealing with a solution, must remain constant. So we need to define this term dynamic equilibrium. We need to understand what both of those bits mean. So remembering that this is for a closed system only, dynamic equilibrium is defined as where the rates of the forwards reaction equals the rates of the reverse reaction. In other words, the concentration doesn't change, but the reaction has not stopped. The best analogy of this is thinking about running on a running machine. You're still running in a forwards direction, and the machine is also moving in a backwards direction, but the rate of your running forwards is equal to the rate of the machine going backwards. So you are not changing position, but you certainly haven't stopped. So thinking about what factors we need to keep constant, those are the factors that can affect the position of an equilibrium. So we have temperature, we have concentration, and for gases we have pressure. And those are generally the three things that will affect the position of our equilibrium. We need to introduce an idea called Le Chatelier's principle. And this principle basically states that if we make any changes to our system, the system will try to counteract that change and move in the opposite direction to cancel out that imposed change. It won't totally cancel it out, but it'll move in that direction. So for example, if we increase the temperature, the system will shift so to reduce that temperature. If we increase the concentration, the system will shift to reduce it. Increase the pressure, the system again will shift to reduce the pressure. So let's look at what this effect would have on a particular system. So here I have this reaction, it's reversible, and the delta H value is telling me it is endothermic in the forwards direction. So as it goes forwards, the reaction gets cooler. That must mean that as it goes backwards, it would get hotter, because if it's endothermic in the forwards direction, it must be exothermic in the reverse direction. So if it's plus 31 going that way, it will be minus 31 going that way. Same magnitude, but a different sign. So if we decrease the temperature, the system will try to counteract that change by increasing the temperature. Well, if it shifts forwards, that's not going to help, because that's just going to make the whole thing colder. So the system will counteract the decrease in temperature by shifting backwards, decreasing the pressure. So on this side, I have 4 moles of gas. On this side, I have 0 moles of gas. So this side has a lower overall pressure, if you like, than this side. So if we decrease the pressure, the system will try to counteract that change by going to the side with the most moles of gas. In that case, this again is this backwards reaction, so this equilibrium position would shift backwards. Last but not least, if we remove this compound CH3CN from the mixture, well, that's going to have the effect of reducing this concentration. If we reduce this concentration, the system again will try to counteract that change. This time it will shift forwards to try and replace the CH3CN. So we can talk about left-hand side, or we can talk about forwards or backwards. It's really up to you, as long as you're clear about which way you are shifting. So let's look at another couple of examples. At the top of page 5, we had hydrogen peroxide decomposing into oxygen and water. In this case, the forward reaction is exothermic. So in this case, if I decrease the temperature, the reaction will shift forwards, because it's going to try and replace that lost heat by shifting to the exothermic side. If we decrease the pressure, it will shift to the side with the most moles of gas, where you have no moles on this side, but 1 mole on this side. So decreasing the pressure will shift to the side which increases the pressure, and that's the side with the most number of moles of gas. So again, it would shift forwards. So here again, we talk about shifting forwards or shifting to the right-hand side. So our last example is looking at the equilibrium between iron 1 chloride, iron 3 chloride and chlorine. So here I have my iodine crystals, and they're reacting with the chlorine gas coming in for the first reaction, and I'm making this brown ICl liquid, this iodine chloride liquid. That will convert into the solid yellow crystals of ICl3 as we're adding more chlorine. Adding more chlorine is going to push the equilibrium position forwards. If we tilt it on its side and don't add any more chlorine, if we remove the excess chlorine, then the equilibrium position will shift back and we will get the brown liquid of iodine chloride. So missing out the practicals on the next couple of pages, we're now on to page 8, and we're looking at an industrial application of these principles. So if we think about the Haber process, where nitrogen gas and hydrogen gas are reacting reversibly to form ammonia, NH3 there. And in this case, under the conditions that we're operating, ammonia will be a gas. So we've got a 2 there and a 3 there. And I'm going to say that this reaction is exothermic in the forwards direction. So in order to have the highest yield of ammonia, we would expect a low temperature, because that's going to drive the equilibrium position forwards, and we would expect to have a high pressure, because that, again, I've got 4 moles of gas on this side, 2 moles of gas on this side, so having a high pressure is going to drive it to the side with the least number of gas moles. So when we run our little simulation, we get a temperature of about 376 and a pressure of 600 to get us the highest production rate of ammonia. But that's not how most plants are run, because that is very, very expensive. We actually want to produce ammonia at the lowest unit cost. Now you can see here the temperature stays roughly the same, drops a little bit but not too much, whereas the pressure rapidly decreases, it more than halves, and that's because running very high pressure systems is costly. It's costly in terms of electricity, it takes a lot of money to run the compressors, and safety wise, if a high pressure system goes, that's a lot more damaging than a lower pressure system. It's still well above atmospheric pressure, but it's not as high as 600. So there are other factors which we need to consider. The cost, not only of running a high pressure system, but also building and maintaining it, safety, and the environmental impact. And in fact, in industrial processes, we generally use a compromise between equilibria and rate. That is why the temperature is higher than you would expect it to be. We need a high temperature so that we produce the ammonia at a sufficient rate. The other reason we usually use a high temperature is the catalysts. Catalysts are very important in industrial processes and usually allow us to run at lower temperatures. But the catalysts do need to be warm, usually to operate efficiently. In the last bit of this section, we're just looking at stored methane. So methane can be trapped in solid methane hydrates. But if you notice, this is an endothermic reaction. So as the methane hydrate warms up due to global warming, it produces more methane. Methane is a very powerful greenhouse gas which warms everything up, releasing more methane from the methane hydrate. So it's a real problem because it's a positive feedback cycle. So that finishes this part of the notes, just looking at an introduction to equilibria, focusing on Le Chatelier's principle. Le Chatelier's principle is the idea that if you impose any change on a system at equilibrium, it will counteract that change. So if you add heat, the system will try to take away that heat by cooling down. Increase the pressure, the system will shift to the side with the least number of gas moles, reducing the pressure. If you increase the concentration of something, either a reactant or a product, the system will try to counteract that change by shifting in the opposite direction. You can kind of think of it like a recalcitrant teenager. Whatever you do, they will want to do the opposite. So, until next time, take care, stay safe. Bye-bye.